Imagine a place where the wind never stops, where storms have been raging for longer than any civilization has existed, where the cold is so absolute, so total, that the very concept of warmth becomes meaningless, where the atmosphere itself behaves like nothing else in the known universe, violent, dark, electric, and alive in ways that challenge everything we think we understand about planets. That place is Neptune. And what happens inside its atmosphere is so extreme, so bizarre, so far beyond anything you can picture that by the time this video ends, you will never look at the night sky the same way again. Neptune sits at the very edge of our solar system's planetary family, nearly 4.5 billion kilometers from the Sun. It receives almost no heat from that distant star. And yet, despite that frozen isolation, Neptune radiates more energy outward than it receives. Something inside this planet is generating its own heat. Something deep beneath those blue clouds is driving a machine of chaos that has been running for billions of years without pause. The winds on Neptune move at speeds exceeding 2,100 kilometers per hour. Let that sink in. 2,100 kilometers per hour. That is the fastest wind speed ever recorded on any planet. It is nearly twice the speed of a military jet fighter at full throttle. But unlike a jet that crosses a continent in a few hours and lands, these winds never stop. They circle an entire planet, a planet 4 times wider than ours, without end, without rest, without slowing down. But speed is just the beginning. Neptune's atmosphere is made of hydrogen, helium, and methane. And it's that methane that gives Neptune its stunning, almost hypnotic blue color. Methane absorbs red light and reflects blue light back into space, painting the planet in a shade so vivid, so pure, that scientists once thought they were looking at liquid water from a distance. They were not. What they were looking at was something far stranger. Beneath those beautiful blue clouds lies a layer of the atmosphere so hot and so pressurized that the very chemistry of matter begins to break down. At a certain depth, the methane molecules are torn apart by pressure and heat, and the carbon atoms inside them, freed from their molecular bonds, begin to compress. They compress so hard, under pressures millions of times greater than what exists at the surface of Neptune's outer clouds, that they crystallize. They become diamonds. Actual diamonds falling like rain through the interior of Neptune, sinking slowly toward the core through a liquid ocean of bizarre compressed matter. Diamond rain on Neptune. Right now, as you watch this video, diamonds are falling inside that blue planet you can barely see in the night sky without a telescope. And we have only scratched the surface. In the chapters ahead, you're going to go deeper into Neptune's atmosphere than any probe has ever gone. You're going to understand why Neptune's storms are fundamentally different from any storm system we can observe elsewhere. You're going to see how a storm the size of an entire planet appeared, dominated Neptune for years, and then simply vanished, disappearing in a way that defies our models and still has scientists arguing today. You're going to learn why Neptune's atmosphere is considered by planetary scientists to be the most extreme, the most violent, and the most scientifically mysterious atmospheric environment in the entire solar system. Not Mars with its global dust storms, not Jupiter with its iconic Great Red Spot. Neptune, this pale blue giant, silent and distant, spinning in the dark at the edge of everything, is the king of catastrophic weather. And the reason you have probably never heard just how extreme it truly is comes down to one simple fact. Neptune is so far away, so difficult to study, so expensive to reach that we've sent exactly one spacecraft past it in all of human history. One. a single flyby in 1989. Everything we know about Neptune, every discovery, every mystery, every jaw-dropping fact you're about to hear comes from that brief encounter, from telescopes straining across billions of kilometers, and from physics and mathematics trying to fill in the gaps. We are essentially trying to understand the most extreme atmosphere in the solar system using almost no data. And what we found, even with those limitations, is extraordinary. Stay with me. Subscribe right now if you're not subscribed yet, because this journey goes deep and you don't want to miss a single second of it. Drop a comment below. Tell me, did you know Neptune had the fastest winds in the solar system? Because most people have no idea. Let's go.
To understand what makes Neptune's atmosphere so extreme, you need to understand something that seems paradoxical at first. Neptune is cold, brutally, incomprehensibly cold. The temperature at the top of its cloud layer hovers around -214 degrees Celsius. That is colder than the surface of Pluto on its coldest day. That is among the coldest temperatures of any planetary surface or atmosphere in the solar system. And yet, Neptune has the fastest winds anywhere. That paradox is the key to everything. On most planets, weather is driven primarily by heat from their star. The star heats the surface or the upper atmosphere unevenly. Warm regions rise, cold regions sink, and that circulation creates wind. The bigger the temperature difference, the more violent the weather. Simple, logical. Neptune receives almost no heat from the sun. At that distance, sunlight is roughly 900 times weaker than what strikes the inner solar system. By any conventional logic, Neptune should be a dead world atmospherically, cold, still, quiet, frozen into a permanent and featureless calm. Instead, it is the opposite of calm. The reason is that Neptune generates internal heat, lots of it. The planet radiates approximately 2.6 times more energy into space than it receives from the sun. This means there is a powerful heat source deep inside Neptune, left over from the planet's formation billions of years ago, slowly leaking outward. And as that heat rises through the planet's layers, it creates convection, massive churning columns of rising hot material and sinking cool material on a planetary scale. But here's what makes Neptune's situation uniquely violent. Because the sunlight arriving at Neptune is so weak and so uniform across the planet, it creates almost no temperature variation across the cloud tops. On most planets, the poles are colder and the equator is warmer. That difference drives circulation in predictable patterns. On Neptune, sunlight is so faint it barely registers. So the atmosphere has almost no guide from above telling it how to organize itself. The internal heat drives the convection, but without strong solar forcing from above to organize that energy into structured, stable patterns, the atmosphere becomes chaotic. The energy goes everywhere. It builds without a stable outlet, and when it finally does find expression, it becomes wind, not gentle wind, not even storm force wind. Wind so fast it breaks every record in the planetary science books. The jet streams on Neptune travel westward, opposite to the direction Neptune itself rotates. This is called retrograde wind flow, and it is deeply unusual. On most planets, the dominant winds flow in the same direction as the planet's rotation. On Neptune, the winds fight the rotation. They go against the planet itself. Scientists believe this retrograde flow is connected to the extreme speed. The internal heat driving convection from below interacts with Neptune's rapid rotation in a way that generates these massive westward jets. And because there is nothing to slow them down, they accelerate to those extraordinary speeds and stay there. Now let's talk about storms.
because Neptune doesn't just have wind, it has storms of a scale and violence that make other planetary storm systems look timid by comparison. In 1989, when Voyager 2 made its historic and only flyby of Neptune, the spacecraft photographed a structure in the southern hemisphere that immediately drew comparisons to Jupiter's Great Red Spot. Scientists called it the Great Dark Spot. It was an anticyclonic storm, a massive rotating system of high pressure, roughly the size of the entire planet we live on. Its winds at the edges were measured at over 2,400 kilometers per hour, faster even than Neptune's already extraordinary average wind speeds. The Great Dark Spot had clearly been there for some time. It had structure, organization, stability. Voyager photographed it in detail, and scientists settled in to study it for years, expecting it to be a permanent or at least semi-permanent feature of Neptune's southern hemisphere, the way the Great Red Spot has dominated Jupiter for centuries. 5 years later, the Hubble Space Telescope pointed its cameras at Neptune. The Great Dark Spot was gone. Not faded, not shrunken, gone, vanished completely, as if it had never existed. This was stunning. Jupiter's Great Red Spot has persisted for at least 350 years and possibly much longer. Neptune's storm, equally massive, apparently stable, had disappeared in less than a decade. And then it got stranger. A new dark spot appeared in the northern hemisphere. Hubble recorded it, and then that one began fading too. Neptune's storms form, grow to planetary scale, and then dissolve on timescales that are almost incomprehensibly short on planetary standards. Why? The current leading theory involves Neptune's cold cloud tops. Unlike Jupiter, where the cloud layer is relatively warm and stable and acts as a kind of floor that traps large storm systems, Neptune's cloud tops are extremely cold. As a storm rises and pushes into the upper atmosphere, it encounters that cold layer, and the storm's structure begins to break down from the top, destabilizing the entire system until it collapses. In other words, Neptune is so cold at the top that even its monster storms cannot survive their own size. That is the kind of world we are dealing with. Storms born violent, growing to continental scale, and then destroyed by the very atmosphere that created them. We talked about diamonds. Let's go back there, because the diamond rain phenomenon on Neptune is one of the most mind-bending discoveries in modern planetary science, and it connects directly to understanding what Neptune's deep atmosphere is truly like. The outer atmosphere of Neptune, the part we can observe, is made primarily of hydrogen and helium, with methane mixed in. That methane is what gives the planet its blue color, but it is also the starting point of one of the most extraordinary chemical processes in the solar system. As you descend into Neptune's atmosphere, pressure increases rapidly. By the time you reach what scientists call the ice giant mantle, a deep layer beneath the outer cloud decks, pressure reaches millions of times the atmospheric pressure at Neptune's cloud tops. Temperatures in this region reach thousands of degrees Celsius. This is not a contradiction. Extreme pressure and extreme cold at the surface can coexist with extreme heat and pressure deeper down. The pressure itself generates the heat. At these conditions, methane molecules cannot hold themselves together. The bonds between carbon and hydrogen atoms break. The hydrogen escapes upward. The carbon is left behind, and under millions of atmospheres of pressure, carbon atoms have only one place to go. They compress, they organize, they crystallize into the hardest known naturally occurring structure in chemistry: diamond. Experimental physicists have actually reproduced the conditions of Neptune's deep atmosphere in laboratory settings using laser-driven shock experiments. They took samples of materials similar to Neptune's interior composition, compressed and heated them to equivalent pressures and temperatures, and watched with X-ray imaging as diamond crystals formed and began to sink through the surrounding material. The experiment confirmed what theoretical models had suggested. Diamond rain is not a poetic metaphor. It is a physical reality happening right now inside Neptune. The diamonds that form are not tiny specks. Models suggest they can grow to significant sizes as they sink toward the core, accumulating over millions of years into what may be a massive diamond layer surrounding Neptune's rocky core, a shell of compressed carbon unlike anything naturally found anywhere else in the solar system. Neptune's core itself is believed to be a rocky silicate and iron structure, roughly the size of a significant planetary body. Above that core sits the deep mantle of hot compressed water, ammonia, and methane ices. Not ices in the freezing sense, but in the chemical sense, compounds that planetary scientists call ices regardless of their temperature because of their molecular structure. And that interior is electrically active in ways that are still poorly understood. Neptune has a magnetic field, but unlike most planetary magnetic fields, Neptune's is dramatically tilted and offset. The magnetic axis is tilted at 47 degrees relative to rotation axis, much more than most planets. And the center of the magnetic field is not even close to Neptune's geometric center. It is offset by more than half the planet's radius toward one pole. This produces a magnetic field that tumbles and rotates in a completely irregular pattern as Neptune spins. This produces an enormously complex magnetosphere that shifts and churns in ways that are almost impossible to model. And because the magnetic field interacts with Neptune's atmosphere, particularly with charged particles in the upper atmospheric layers, this adds yet another layer of complexity to an already chaotic system. In the upper atmosphere, above the main cloud decks, Neptune has an auroral system. Auroras, similar in concept to what exists at the poles of other magnetized planets, but wildly unpredictable in location because of that tilted and offset magnetic field. Neptune's auroras can appear almost anywhere on the planet, shifting and flickering as the magnetic geometry changes with each rotation. Now let's talk about Triton. Triton is Neptune's largest moon, and it is almost certainly a captured Kuiper Belt object, a world from the outer solar system that wandered too close to Neptune billions of years ago and was gravitationally captured. Triton orbits Neptune backwards in a retrograde direction, slowly spiraling inward due to tidal forces. In approximately 3.6 billion years, Triton will pass within Neptune's Roche limit, the point at which tidal forces overcome the Moon's own gravitational cohesion, and Triton will be torn apart, its material spreading into a ring system around Neptune. But Triton's relevance to Neptune's atmosphere is more immediate. Even today, Triton's gravity and orbital mechanics influence Neptune's tidal dynamics, which in turn affect the deep interior convection patterns, the same convection that drives those record-breaking winds. Everything in this system is connected. The winds, the storms, the diamond rain, the magnetic chaos, the doomed moon spiraling closer. Neptune is not just a planet, it is a system, a violent, beautiful, deeply strange system that operates on principles we are only beginning to understand. And there is one more thing that makes Neptune unlike any other world in the solar system, something about the way its seasons work, the way time itself moves differently there, that changes how we think about planetary evolution entirely. That is where we are going next.
Neptune's year lasts 165 of our years. Think about that for a moment. One single orbit around the Sun, one Neptunian year, takes a century and a half.
Neptune has completed only one full orbit since it was discovered in 1846. Only one. The planet has not yet had time for a second lap around the Sun since the moment humans first realized it existed. This has extraordinary consequences for its atmosphere and its weather systems. Because Neptune's axis is tilted about 28 degrees, similar in magnitude to other planets, it experiences seasons, but those seasons each last over 40 of our years. The northern hemisphere of Neptune entered summer only recently in terms of Neptune's calendar. And that seasonal shift, that slow, grinding change in how the tiny, distant sun illuminates different parts of the planet is already affecting the cloud structure and storm patterns in ways Hubble and ground-based telescopes are actively monitoring. In recent decades, as Neptune approached and entered its current seasonal configuration, astronomers have observed a surprising warming trend in the southern hemisphere, the hemisphere that is now moving into its long autumn, and unexpected changes in cloud brightness and storm frequency. Neptune's atmosphere responds to its seasons, but those responses unfold across timescales of decades, making it incredibly difficult to study because you need continuous observation across generations of scientists to understand even one seasonal cycle. We have had that continuous observation, barely, and what it has revealed is that Neptune's atmosphere is not static even between the dramatic storm formation and dissolution events. It breathes, it shifts. Cloud coverage increases and decreases. Bright methane cloud features appear at certain latitudes and fade from others. The upper atmosphere cools and warms by small but measurable amounts as the seasons turn across those 40-year intervals. This is a living atmospheric system operating on timescales that dwarf anything humans experience. And here is the most humbling part of everything we have explored in this video. We have only one data point from up close, one spacecraft, one flyby, 1989. Everything since then has been remote observation, telescopes trying to read the weather on a planet 4.5 billion kilometers away. The level of detail we lack is staggering. We do not know the exact depth of Neptune's cloud layers. We do not know the precise mechanisms driving those 2,100 km/h winds. We have theories, good ones, but no confirmation. We do not know exactly how the diamond rain process works at every depth, or how thick the diamond shell around Neptune's core might be, or whether it's continuous or patchy. We do not know why Neptune's great dark spot disappeared when it did, or why the replacement storm in the northern hemisphere behaved differently. We do not have detailed measurements of Neptune's internal heat source, its magnitude, its distribution, its driving mechanism. We're looking at the most extreme atmosphere in the solar system through a keyhole, and even through that keyhole, we're seeing things that break our models and demand new explanations. There's a proposed mission, NASA's Neptune Odyssey concept, that would send an orbiter to Neptune, potentially with an atmospheric probe that could descend directly into those cloud layers and measure in real time what is actually happening inside that blue atmosphere. If this mission were funded and launched, it would reach Neptune in the 2040s. If and when that probe descends into Neptune's clouds, it will be the first direct measurement of that atmosphere in all of human history. We might finally hear what those 2,100 km/h winds sound like. We might directly sample the chemistry of those cloud decks. We might get pressure and temperature readings from depth, readings that will either confirm our diamond rain models or force us to tear them apart and start over. Neptune is waiting. It has been waiting for billions of years, running its storms and its winds and its diamond-generating interior in silence at the edge of the solar system, indifferent to whether we ever understand it or not. But we're getting closer. And what we have already found, without ever entering,
without ever lingering, with just one brief flyby 35 decades ago, is already enough to make Neptune one of the most remarkable objects in the known universe. The fastest winds, the disappearing storms, the diamond rain, the chaotic magnetic field, the 165-year seasons, the doomed moon, the internal heat that defies expectation, the blue that hides violence. Neptune doesn't look dangerous from here. It looks beautiful, a small blue dot in the darkness, serene and distant. But now you know what is happening inside that dot. If this video changed how you see Neptune, if you're going to look at the night sky differently after this, hit that subscribe button right now, because there's so much more to explore. Drop a comment below telling me which fact hit you hardest. Was it the diamond rain, the wind speeds, the vanishing storm? I read every single one. The universe is not empty. It is full of this, and we're just getting started.